The topic of my paper is space debris, and since humanity began to use Earth's orbit for their own purposes, from the launch of Sputnik 1 in 1957, satellites have become more and more vital to every human's life. However, the many uses of these satellites from GPS to television are threatened by what is known as space debris. It's now a large problem and is predicted to become one much more in the near future, due to the fact that this debris will collide with active satellites, causing catastrophic harm. If a plan is not enacted to remove space debris, mitigate its effects, or find some other way to protect satellites, the results will be catastrophic. So, in order to understand space debris, first we have to understand where it is. Currently, NASA, as well as other international bodies, define three areas of orbit. The first, as seen here, is low Earth orbit. This is orbit that is below 2,000 kilometers. This is where most satellites, and therefore most space debris, in fact 43%, lies. This is where a lot of the recovery effort is at. The next circle, which is one of the further orbits, is geosynchronous or geostationary, which is satellites that stay over one area of Earth. That's very useful for communications and weather, as it focuses on one area. And in between there are a bunch of smaller orbits. They are used for various purposes, but not as many are in them. Now let's talk about why space debris is an actual problem. There is an effect known as the Kessler effect, discovered by Donald Kessler in the 70s and proven over and over again, that basically is like a chain reaction. And in this chain reaction, let's say a piece of debris, a paint fleck, part of a space shuttle that fell off, or even other satellites that are just unused, crash into a satellite. This creates debris from the collision. Then, this debris, as we will see, goes around Earth in orbit with everything else. It may eventually fall back to Earth, but not before it has a higher likelihood of running into other satellites, creating more debris, and it keeps going and going and going. And this is a problem, of course, because this means that there'll be more and more debris, meaning we can send less and less up and communicate with our satellites less often. Now, the way that we can prove the Kessler effect, as well as the way that we can predict when satellites may, in fact, crash into each other, is through modeling systems. The first major one of which was EVOLVE. EVOLVE was created by NASA. It was two-dimensional, and it said that Earth was oblate, which meant that the equator, at the equator it's much more bulged out. It noted that the atmosphere rotated due to friction at a different velocity than Earth, and it took into the effects of lunar and solar gravity. However, this was not good enough for long-term prediction, and therefore LEGEND was developed. It was three-dimensional, and it had many more innovative features, such as using a Monte Carlo simulation to allow averages to develop, meaning it was much more accurate. It also had better tracking, so it could track latitude and longitude of debris, as well as altitude. And finally, it had a better model for orbital growth, which was more useful for long-term analysis. There are current, yet temporary ways of dealing with space debris that is considered catastrophic or greater than 10 centimeters. That which we can track, there's 22,000 in low Earth orbit and hundreds in geosynchronous orbit. This is the most dangerous because it can provide catastrophic results. Currently, for debris under 1 centimeter, we have shields. They are basically just what they say they are. They block debris from hitting the satellite by bouncing it off. Next, for larger debris, we have maneuvers. Many satellites have boosters on them in order to dodge incoming debris that is large enough to be tracked, and NASA does report this to companies as well as, of course, their own satellites. But this is not a permanent solution, as we will not have enough fuel on satellites and eventually they'll run out, and also because of larger projects such as the International Space Station requiring huge amounts of preparation. So, many companies and researchers have decided to look at active removal methods, of which there are many. The most common of which is a propulsion-based retrieval satellite, of which a tether or net is attached, and where it flies out, grabs the space debris, and jettisons it back down to Earth or back towards a sort of recycling center. However, there are other ways, such as the use of the Earth's electromagnetic field to propel a satellite using electrodynamics in order to catch large debris. This is more fuel efficient as it would not require fuel at all. However, a net is not the only method of retrieval. There are a couple others and more being developed every day, one of which, proposed by Japanese Aerospace Exploration Agency, actually uses net charge to repel debris until its orbit gets smaller and smaller and smaller and it falls back to Earth. This might need new technology, however, it could potentially be more cost-effective. Much more cost-effective than a net. However, another idea could be to create new shields that are effective for debris that's above 10 centimeters and therefore catastrophic if it were to collide. These new shields require new materials, but would definitely be more cost-effective than actually removing the debris. The downside of this is the materials engineering might take time, and the debris would eventually pile up so much that this would not work. My research proposal would be for students at Embry-Riddle Aeronautical University Prescott campus doing their senior design capstone project would split into teams of 6 to 10 members to have at least 2 mechanical engineers, preferably at least one with a propulsion track, 2 electrical engineers, so that they can determine electrodynamics if they choose to do so, as well as work on the electronics of the retrieval device, and they would need at least 2 aerospace engineers to help get it up there and to determine how orbit affects that. There could be more options of more engineers as well as global business majors to develop feasibility and business plans of these designs. All the students should have pre-existing general knowledge of space debris as well as current proposed solutions. The strengths of this design is that it would allow students to come up with their own proposals on how to remove space debris, and it would allow for new ideas that perhaps haven't been tested to actually be tested, as well as confirm other ideas and their cost effectiveness. The expected results is that debris shield improvements would probably be the most effective way, but the others could potentially surprise and in fact be better due to their ability to actually remove space debris. My method of this research was archival research through EagleNet as well as ProQuest. However, I also looked through NASA journals as well as sources on my previous sources. And that's it for my research. Thanks for listening.